Hi all. I kind of needed a change, so today we're solving a change. So today we're solving a past paper from England. Okay, at least I believe so because uh, this is the paper one, Advanced Physics one, of the Edexcel curriculum, which means that it's not the curriculum of the International Edexcel. But from what I saw, papers 1, 2, and 3 of the Edexcel curriculum for the UK are pretty much the same, or maybe it's a combination of Unit 1 through 6 papers of the international test, meaning that in paper 1 you will see many questions that are relevant to Units 1, 2, 3, 4, 5, 6, okay? So this video is also useful to those of you who are taking the international test, okay? But anyway, this is, I believe, the UK test, and please let me know in the comments if I'm right about this, and if you want to see more papers from Edexcel or the International Edexcel, etc. Okay, so far I'm only doing physics videos, but at least on paper I can probably do mathematics papers and so on. I haven't looked into that yet, to be honest. Okay, so this was the most recent paper I was able to find from May 2025. I don't remember how I found it. I think I just Googled it, and I was able to find both the paper and the mark scheme, but the solutions are mine, okay? I mean, I always go through the papers, so I have a personal feeling of what's going on. So with all this being said, let's dive in. With question 1, the first 10 questions are multiple choice, so let's do that. Which of the following was investigated by the large angle alpha particle scattering experiment? Option A is the structure of an atom. Okay, that sounds reasonable. I mean, that sounds like the probable answer. Structure of a nucleon, no. Structure of a nucleus, no. Structure of a quark, no. So A is the correct answer. Question 2, which of the following is a scalar quantity? Okay, as you can see, options B, C, and D involve vector quantities, displacement, electric field, force. So A, charge, which is, yeah, I mean, there is no direction to charge, right? Question 3 now. A ball is tied to the end of a length of string. A person holds the other end of the string. The person spins the ball and the string around in a horizontal circle as shown. Which of the following statements best describes, why the person feels a force from the string? Okay, before we see the options, what's going on here? There is the tension, right, from the person who is holding the string and spinning it, and there is a ball attached to it. And therefore the ball, I mean, we have two objects here, right, 1 and 2. And via Newton's third law, we know that the ball also pulls the person in the opposite direction towards the ball via the same force T, the tension, right? So this is Newton's third law. Okay, let's see the options. Which of the following statements best describes why the person feels a force from the string? Option A, there is a centripetal force acting on the person. No. B, there is a force on the person due to Newton's first law. Newton's first law has nothing to do with force, okay? It has to do with motion, okay? C, there is a force on the person due to Newton's third law, okay? That's the answer, right? And D, there is a force on the person due to the weight of the ball. No. So, let's move on. Question 4. A wire of resistance R has a circular cross-sectional area. A second wire has the same length and it's made of the same material. The diameter of the second wire is double the diameter of the first wire, okay? Which of the following is the resistance of the second wire? Okay, let's write down the resistance of the first wire, okay? It's made from some material that has resistivity, let's call it rho, okay? Times its length over the cross-sectional area, which since you're given the diameter, we can write the cross-sectional area, it's circular, right? So that's pi d squared over 4, right? So the 4 moves to the numerator, but okay, let's keep it like that. Now for the second wire, R prime is given by rho, since it's the same material, has the same resistivity, same length, but now we have twice the diameter, right? So we have let's write down the formula. So pi d prime squared over 4, but d prime is 2d, so that's rho L pi 4d squared over 4. So let me use a clean page. If we divide r by r prime, we will find we have rho L and then pi d squared over 4. And in the denominator we have rho L pi d squared, and then we have the 4, and then we have another 4 there, okay? So, is that correct? Yes. So this cancels, these cancel, pi cancels, d squared cancels, and we are left with 1/4. Okay, so the option is D. Okay, I hope this makes sense. Now, let me see. We can actually substitute here. We can also see that this, oops. So if we pick, let me see. Okay, if we pick this part, this is R, right? And we have 4 in the denominator. So that's an easier way to see that R prime is R over 4. And actually here I made a mistake. This should be R over R prime is 4. Okay. Sorry, I'm a human. So this is 4. So we're actually looking for R prime over R, which is 1 over 4. All right, question 5. A positron produced a track in a detector as shown. Which of the following is the direction of the magnetic field in this detector? Okay, let's first reason which was the direction of motion, okay? So we see a spiral that kind of curls inwards, right, like this, okay, which means that the direction of motion is that one, okay? Which means that the linear velocity is tangent to the curve, to the circle, right? So that's the linear velocity of the particle, okay? And the force is in this direction, right? Because you have a centripetal force. So that force is equal to QVB, and we can use Fleming's left-hand rule with our index pointing in the direction of B. The middle finger should point in the direction of the velocity, and the thumb should point in the direction of the force, okay? What did I do there? So that's supposed to be an M. I'm sorry, guys. If you are watching from England, I'm really curious to read your comments about how I teach, my pronunciation of English, and so on. So anyway, okay. So if we put, let's try. If we put our index finger into the page, okay, in this direction, right? So if B is inwards, so if we put our left index finger pointing into the page, and then we put our middle finger in the direction of V, then we see that our thumb points inwards. So that's the answer. So B is into the page, and the answer is B, incidentally, okay? So, hope this makes sense. Let's move on to questions 6 and 7. Refer to the information below, I guess, the circuit, okay? A high voltage DC power supply was connected to the parallel metal plates and an ammeter as shown. Okay, question 6. The distance between the two plates was decreased, so they brought them closer together, right? Which row of the table is correct? So this is the positive end of the power supply, and this is the negative end, which means that Q is the negative end of the capacitor, and P is the positive. So the direction is of the field is from P to Q. Okay, so either A or C are the correct answers. Now the electric field strength is given E for parallel plates only. E is given by the voltage of the power supply over the distance, right? So if D decreases, E increases. Therefore, the answer is C, okay? Let me erase that and let's move on. Now, question 7. I will explain. I think it's easy, but I will explain why. So, question 7, decreasing the distance between the plates increases the capacitance of the two parallel plates. Okay, the separation was decreased at time x, and at time y, the separation became constant. Which of the following graphs shows how the reading I on the ammeter changed with time t? Okay, so the background information for this one is that if we charge or discharge a capacitor, actually let me write I, okay? So for charging or discharging, the current goes to 0, okay? So in this case, initially the capacitor is charged, right? So I is equal to I naught e to the minus t over the time constant for this circuit, and the time constant is RC. They don't have a resistor here, so it's kind of a dangerous circuit. But anyway, that does not concern us for this problem. So I'm trying to say that the current is 0. So, so the separation was decreased at time x. So at time x, they started decreasing the separation. So they started bringing these plates together. Okay, so the current before should be 0. And at time y, the separation became constant, meaning that they stopped moving the plates, which means that the current, again, should be 0. So the only possibility here is C, right? Nothing else makes sense, because here we have some current while the capacitor is fully charged. Same for this one. For this one, we have current when the capacitor is charged again. So this makes no sense, okay? So C is the correct answer. So yeah, I tried to explain it conceptually. So for those of you who are first timers in my videos, this is what I try to do. I try to explain the physics behind the problems. I kind of like it as well. I mean, I'm a physicist, so I studied these things. So anyway, all right. So question 8. The initial potential difference PD across a capacitor is V naught. The capacitor is discharged through a resistor. The potential difference across the capacitor decreases to V naught over 3 in 2 milliseconds. Which of the following is equal to the time constant in milliseconds for this capacitor resistor circuit? So let's use the capacitor discharging formula, which is a decay. V is V naught e to the minus t over tau. Okay, so we are interested in tau. So before we plug in anything, let's solve for tau. So we have e to the t over tau is equal to V naught over V, right? Yes. The way to do this, by the way, is to multiply. You multiply the right-hand side with e to the t over tau, and then you multiply the right-hand side with e to the t over tau. So you have e to the t over tau times e to the minus t over tau, which cancels to 1, right? Because you have e to the t minus t over tau, which is to the 0, which is 1, okay? Just to explain what I'm doing. So, okay. So we take the ln of both sides. So t over tau is ln of V naught over V. So tau that we are interested in is equal to t over ln of V naught over V. So we are told that the potential difference across the capacitor decreases to V naught over 3 in 2 milliseconds. So let's plug in the numbers. So in 2 milliseconds, tau is 2 milliseconds over ln of V naught, which is the initial voltage, over V naught over 3, right? Which is equal to 2 over ln, this V naught cancels. We have 1 over 1/3, which simplifies to 3, okay? So the answer is B. Okay. Questions 9 and 10 refer to the information below. A ball was thrown so that it followed the path shown. Assumed drag forces were negligible. Which of the following is a free body diagram for the ball at its maximum height? It doesn't matter if it's at the maximum height or not, because in the y direction, so if you take axis as x and y, okay, in the x direction you have no forces acting since there are no drag forces, and in the y direction you have the weight pointing down at all the points. And actually the vector should be of equal length, so something like this. So at the top or bottom, it doesn't matter. The answer is D. Okay, hope this makes sense. Now, question 10. Which of the following graphs shows how the vertical component of velocity v subscript v varies with time t when the ball is thrown to just before it hits the ground? Okay, I'm going to use a clean page to explain this. So initially we have this situation. The ball is thrown under some angle theta to the horizontal, and it has some initial velocity u. Okay, we have two components for the velocity, the vertical component and the horizontal component. The horizontal component is u cosine theta, because this component touches the angle theta. That's how I explain it. And the component that doesn't touch the angle theta, you see there is no physical touch between this component, the vertical component theta. That's that's u vertical, the initial velocity in the vertical direction, is equal to u sine theta. Okay. What kind of formula can we use to explain we're given the graph of v versus time. So the most useful that equation is v is equal to u plus at. In our case, we have v vertical equals to u vertical plus the acceleration. What's the acceleration? Minus g, right? Because we are moving in gravity and the velocity points up, but the gravity points down. That's why the minus sign, okay? So this is equal to u sine theta minus gt. And if you plot this at time equal to 0, so this is v and this is t, at time equal to 0, we have u sine theta. And then we have a negative sloped curve, so it will look like this, right? Which option is that? A. All the other options make no sense. Okay. I'm gonna sip my coffee, I guess, so I'll be back in a moment. Okay, I'm back from my coffee break. So, question 11. Diodes are used in a variety of electrical circuits. Question A, sketch the current potential difference graph for a diode. All right, so you see, for example, that I believe that for the international test, this is in unit 2, I believe. But anyway, so let's draw the graph, okay? So there is some potential difference, okay, after which current can flow in the circuit, okay? So before that, so there is a small slope. It's almost 0, but not exactly 0. Okay, something like that. And then it spikes up. So that will be the graph, okay? So, oops, let me try to fix that. So something like that, okay? So you need some minimal potential difference and then current starts flowing in a diode. So Moving on. Okay, part B. A package containing a light emitting diode LED is marked 20 milliamps, 3.2 volts to operate normally. A student uses a 5-volt power supply of negligible internal resistance to operate the LED. Calculate the resistance of a protective resistor required to operate the LED normally from this power supply. So the circuit would look something like this. So this is the resistor, and this is the LED. Okay. So, and you connect the 5-volt supply. Okay, so that's your 5 volts. So you need VR pretty much, plus this is the V of the LED. Okay. You need that to sum to 5 volts pretty much. So VR plus VLED must be 5 volts. VLED for operating the LED normally is 3.2 volts. It's given, right? So VR must be 5 minus 3.2 or 1.8 volts. And also the current, the safe current is 20 milliamps, right? So VR is IR equals to 1.8 volts. So R is 1.8 over I, and I is 20 milliamps, so 20 times 10 to the negative 3. So that's 90 ohms. And that's the resistor that you need. All right, moving on to question 12. The photograph shows a lever arm balance. The balance can be used to measure the mass of objects to the nearest gram. The lever arm is a length of metal bent on one end and as shown in the diagram below. The lever arm can rotate around the pivot P. Okay, so I guess the pan can come down this way and the lever arm can come up. Wait, let me see. So it comes up, yeah, this way. Okay, so this is how it works. So the arrangement is in equilibrium. Okay. State the two conditions needed for the arrangement to be in equilibrium. So sum of all forces must be 0, and sum of all torques must be 0. So about any point. Okay. So sum of all forces and sum of all moments. Okay, I said torques, moments. Okay, so it's the same thing. So part B, determine the weight of the counterweight. Assume the mass of the lever arm is negligible and the mass of the pan is 260 grams. So I'm gonna come here so I explain what I'm doing. So pretty much we have to take the weight of the counterweight. Okay, so let's make it straight down. Okay, so that's the weight. We have to analyze this into this component that is perpendicular to the arm, right? So this creates a moment, right? And there is also this component. So this component, this one that I'm pointing with the green arrow, creates a moment about P, whereas the other component, go back, there's also this component over here, but that component is along the lever, so it doesn't really create a torque because it points straight at P. Okay, so now we also need the angle. So this angle is 80 degrees. Okay, and the way to know this is to realize that let me see, this arm and this are perpendicular, and then the weight, this side is perpendicular to that side. Therefore, the inscribed angles are both 80 degrees. I hope this explanation makes sense. If it doesn't, I can try again and explain it in the comments. But let's move on. So We now have two torques about the point P. This component over here, which is mg cosine 80 degrees, and then the weight of the pan, right, which is simply mg. Okay, and mg acts from 0.04 meters away, whereas mg cosine 80 degrees acts from 0.18 meters away. So we have to find the moments about P. So m of the pan times g times 0.04 must equal the mass of the counter arm times g times cosine 80 degrees times 0.18. G conveniently cancels, and if we solve for capital M, we find M is equal to M of the pan times 0.04 over 0.18 times cosine of 80 degrees. And this is 332.7 grams, or about 0.33 kilograms. That's the answer. That's not the answer. We are asked to determine the weight of the counterweight, okay? So the weight, so let's write 0.33 kilograms there. So the weight is m times g. Okay, so 0.33 times 9.81, which is 3.26 newtons. Okay, C. An object is placed in the pan. The lever arm moves along the scale. Explain why the lever arm pointer moves through a large distance whilst the pan moves a much shorter distance. Okay, so to understand this, maybe I should draw it again in a clean page. So this is the pan, right? And that's the pivot P, and you have a lever arm, and you have a counterweight, something like this. Okay, so if this rotates, let's say it rotates and comes here, okay? So that's the pan in the new position, and that's the angle theta. Now observe how big the change will be for the lever. So something like this. The lever will be up here, okay? So that's theta again, but this arc length is much bigger than this arc length, okay? And the reason is because this radius is larger. So let's write this down. Since the arc length is equal to S, and S is equal to R times the angle theta, then because, so the S is this thing over here, so that's S, and that's also S prime, I mean for the lever pan, okay, because this is 0.04 meters pretty much, whereas this is 0.18 meters, okay? So then because for the arm, R is 0.18 meters, but for the pan, let's call it R prime is 0.04 meters, comma, then S for the arm will be larger than S prime for the pan for the same theta. Okay, that's the answer. Let's move on. Question 13. Solar cells. I come from Cyprus, and solar cells are en vogue, as we say. People are obsessed with solar panels because they think they can make free energy, blah, blah, blah. I don't know. I'm not a big fan. I'm a nuclear physicist by training, so I'm pro-nuclear power, not solar power. So anyway, let's read the question though. So solar cells are being used. By the way, write in the comments whether solar cells can be used in England, because I've never been to England, but there is this rumor, not rumor, I mean this idea that England is cloudy and so on. So I'm curious if people use them. So let me know in the comments. So solar cells are being used in increasing numbers around the world. The current I from a solar cell can be varied by connecting it to a variable resistor. Okay. The graph shows how I and the terminal potential difference V across the solar cell vary. Question A. Complete the circuit diagram below to show how the data for the graph could be obtained. Okay, so first of all, we need a variable resistor, right? I'm in my sister's office. My sister is a lawyer, by the way, so people come and go. That's why you probably hear some noises sometimes. So that's the variable resistor. We also need to connect an ammeter in series with the solar cell to measure the current. And we also need a voltmeter, let's connect it there, to measure the voltage across the solar cell. Okay. B, show that the maximum power output for the solar cell is about 2 watts. You should use values from the graph. Okay, there are 2 ways to do this. One is easy, one is harder, kind of harder. So when you're given an IV graph, the power, we know that power is I times V, which is nothing but the area under the curve, right? But this is not what we want now. We actually want, we are asked for the maximum power output. So, okay. So for the maximum power output, you should take 2 points where both the current and the voltage are kind of maximum. So somewhere there, that's the sweet spot. So I chose this point over there. Okay, so if you go down like that, you see that's 0.54 volts. And if you go horizontally, okay, you see that's 3.4 amps, okay? And if I multiply 3.4 by 0.54, we are gonna find the maximum power, but you can also find the area under the curve, right? So it's the same thing. So P is IV, or 0.54 times 3.4, which is about 1.84, which is 1.84 watts, which is about 2 watts as asked, okay? They are not very strict with choosing those 2 points. I mean, you can choose something else, maybe this point, okay? You will arrive at a similar result, okay? So don't freak out if you're not exact. And check the mark scheme for how precise they want the answer. But I think from my experience, that's good enough. Okay, part 2. The area of the solar cell is 104 square centimeters. Determine the efficiency of the solar panel when operating at maximum power. And they give you the intensity of sunlight. Okay, so the first step is to find what the input power is. So P input is equal to 1000 watts per square meter that comes from the sun times the surface area of the solar cell, which is 104 square centimeters. So we have to multiply by 10 to the minus 2 and then square this to find to convert to meters squared, okay? In case that doesn't make sense, I can write it over here. 1 square centimeter is equal to 1 times 10 to the negative 2, and the whole thing must be squared, meters squared, okay? So if you multiply all these, meter squares cancel, we find 10.4 watts. Now the efficiency is given by the useful power that we produce. Useful means what we produce pretty much. And P input means what's inputted into the system. So we input power from the sun, like sunlight, right, which is absorbed by the whole surface area of the solar cell. And from that input, only 2 watts or 1.84 watts are converted to power, as we found. So 1.84 over 10.4 gives 0.176. And if we multiply by 100, we find 17.7% is the efficiency. Okay, part 3, calculate the internal resistance of the solar cell when operating at maximum power. Okay, this was a little bit complicated for me to understand what they meant, but I went for this solution. So we know that the voltage across a power supply or a power cell or whatever has internal resistance is given by mth minus the current that passes through times the internal resistance R, okay, lowercase r. Okay, in our case, they give us the IV plot, not the V versus I. So it's a little bit involved. So let's solve for I. So I times R is E minus V. So I is mth over the internal resistance minus 1 over R V. Okay, so first of all, the first observation is that for I equal to 0, when the current is 0, so over here, the voltage is that one, 0.58. So for I equals 0, V is 0.58 volts, so we can plug into that equation over here. So if we plug in, we find that 0 is it's E over R minus 1 over R, 0.58 volts. We don't need the volts here, it looks weird. Okay, so R cancels, right? Because R is multiplied by 0, so it goes to 0. So E, the mth, is 0.58 volts. Okay, now the gradient of the IV curve, so I'm going to use a clean page. So the gradient of I versus V curve is 1 over R, actually minus 1 over R, okay? So delta I over delta V is minus 1 over R. So let's go back to the graph. I'm going to erase all this because it got cluttered. Okay, so I'm going to erase this to show you guys what I'm trying to do. So I took again, so we're trying to find the slope of this curve pretty much. Okay, this part of the curve. Oops. I don't know how to make it straight, but okay, let's just draw along. So we want to find the gradient of this curve. Okay, so we're going to use 2 points pretty much. Remember the point we used earlier, this one, and we also use this one. So if we subtract these points pretty much, we will find the slope. Okay, so let me mark down what these values are. So I up there is 3.4 and V is 0.54, and down there I is 0 and V is 0.58. So these 2 points will give us the slope of this curve pretty much. Okay, I hope this makes sense. If it doesn't, again, ask me in the comments. I always reply to comments from students all over the world. I'm happy to do that. So let's go over here. So let's use black again. Okay, so minus 1 over R is equal to delta I. So 0 minus 3.4. Okay, and then denominator we have 0.58 minus 0.54. So this yields R is equal to 0.012 ohms. Okay, I went a little bit fast maybe, but I can show you. So minus 1 over R is minus 3.4 over 0.04. So R, the minus cancels, so R is 0.04 over 3.4, which yields 0.012 ohms. Okay, this was a little bit harder, but doable. I mean, it's a problem. So, moving on to question 14. Flowers can attract bees by being colorful or by producing a scent. Some flowers also attract bees by producing an electric field. Honestly, before solving this paper, I had no idea that this is the case, okay? So you learn something new every day, okay? I mean, and this is the spirit, I guess, guys, I mean, for your whole life. So anyway, draw the electric field around a negative point charge, okay? So if that's negative, the electric field points into the charge, right? So those are the electric field lines. It's point charge negative, so everything goes in. All right, B. When a bee gets close to a flower, it can detect the electric field. The charge on the flower acts as a point charge at the center of the flower. At a distance of 0.06 meters from the center of a particular flower, the potential is minus 16 volts. Show that the charge on this flower is about minus 0.1 nanocoulombs. Okay, so here we have to use the potential equation. So the potential of a point charge or a sphere that is charged, or in general spherical distributions of charge, is 1 over 4 pi epsilon naught times Q over R. So Q is 4 pi epsilon naught times R times V. Okay, now K is 1 over 4 pi epsilon naught. Therefore, 4 pi epsilon naught is 1 over K, which we will plug in. So Q is V times R over K, or what are the units again? So minus 16 volts. And here I'm going to show you how you work out the units. So the way I solve problems, when I plug numbers into formula, I put all the numbers to the left and all the units to the right. So we plugged in for V, so minus 16 volts. So I put volts to the right. And then R is 0.06 meters, so I put meters there. And then K is 8.99 times 10 to the 9. And the units are newtons meter squared over coulombs squared. All right, so this works out to be minus 1.06 times 10 to the negative 10. And now let's work out the units. So meters cancels, right? Now 1 volt is 1 joule per coulomb. Okay, so let's write that down. So volt is joule per coulomb. So that's 1 volt. So that's volts, okay? And then we have coulomb squared upstairs, right? And then we have newtons times meters over here. So what's newtons times meters? Joules, right? So let's write joules down there. So joules cancels, and then one of the coulombs cancel to give us the charge as minus 0.1 nanocoulombs as asked. Beautiful, right? So let's move on to part 2. The minimum field strength that the bee can detect is 120 volts per meter. A teacher suggests that bees can detect the field when they are closer than 10 centimeters from the flower in B1. Deduce whether this suggestion is correct. Okay, so the electric field for point charges or spheres is 1 over 4 pi epsilon naught Q over R squared. So let's just plug in numbers, right? So this is K again, right? So 8.99 times 10 to the 9. This time I'm not going to use the units. Everything works out to volts per meter, so okay. Times 0. Sorry, let's use the calculated one. 1.06 times 10 to the negative 10. And then r squared, let's use the 0.1 squared that they tell us. They tell us 10 centimeters, which is 0.1 meters. So, and I'm using the absolute value of E so that the charge is positive, even though we know it's negative. Okay, so this evaluates to 95.3 volts per meter. And as usual, teacher is wrong. Okay, I guess they do it on purpose for fun. Okay, so I noticed that in the A-level tests, the teacher is usually wrong. Right, C. Question C. It is suggested that the hairs on a bee deflect slightly when close to the flower. Explain what will cause a hair to deflect in an electric field. So they must be charged, right? So hair is charged. So hairs, do you say are or is? I think are. Hairs are. It's plural after all, right? So hairs are charged. We don't know, it can be positive or negative, okay? Hence, they are deflected by E, okay? So that's the answer. I mean, there's nothing more to say. It's time to move on to question 15. Whenever I see problems related to nuclear or particle physics, my heart warms because this is what I studied for my PhD. So I kind of love these things. So a sigma plus particle is a baryon. It can decay into a positive pion and a neutron. Complete the particle equation for this decay. So sigma plus goes into a neutron plus a positive pion. Okay, I mean it's simple. They give it to us. I don't know why they ask you to write it down, but that's the answer. Part B. Explain whether the conservation laws of charge and baryon number are obeyed for this decay. So we have a sigma plus going into a neutron plus pi plus. The charge is +1 before and +1 after, since the neutron is neutral. And then the baryon number is 1 because sigma particle is a baryon. So all baryons have a baryon number of 1. Okay. And neutron is a baryon with a baryon number of 1, so they are conserved. Okay, the table summarizes the charges for 3 types of quark. So we have U, D, and S. The sigma particle has 1 strange quark within its structure that uses the quark structure of sigma plus. Okay, so it has 1 strange quark, right, which has a charge of -1/3. Okay, and we need this thing to have a charge of +1. So the only way to do that is if it contains U and U, because we will have +2/3 of charge, which it's 4/3 -1/3, that's 1. Okay, so sigma plus is UUS. Okay, very similar to the proton. Remember, the proton is UUD. Right? So let's move on. You don't need this. I'm going to erase it. Okay, let's move on. D. The diagram shows tracks in a particle detector associated with this decay. Question I. State why the neutron does not leave a track. You see that you have the sigma plus coming in, decaying into a pion that spirals this way, I guess. Okay, and then the neutron should be somewhere here, maybe here, something like that, but it's not shown on the tracks. And the reason is because it's not charged, therefore it doesn't cause ionization. So neutron has no charge, so it produces no ionization. Right. Part 2, the initial momentum of the positive pion is 1.1 times 10 to the negative 19 newtons times seconds. The scale of the diagram is 1 centimeter, represents 15 centimeters. Determine the magnitude of the magnetic flux density acting perpendicular to the tracks. Okay, so the way I worked this out was to first find the radius of the pion when it undergoes this circular motion. So I took this part of the curve. I hope the pen helps me. Yeah, I mean, it's not perfect, but we're gonna make it work. We will assume that this is half the circumference of a circle, sorry. Not a circus, a circle, I'm sorry. That, okay, that has some radius r. What's half the, okay, the circumference of a circle is 2 pi r. So half the circumference is pi r, right? So that's the idea. And they say that 1 centimeter represents 15 centimeters in real life. I mean, 1 centimeter in the diagram. So what I did was, I mean, this is a crude estimation. I actually think that I have a ruler tool here. Let me think, not there. There is a ruler tool that I used in some of my past videos. I can't see it now. Let's see. Not here. Anyway, yeah, here. That's the ruler. Okay. Wait, we can actually use it. So where is the 0? Okay, there. So I guess you can. Another way to do it, I mean, I'm doing this on the fly now, okay? So another way to find the radius is to draw this line here. Okay, and that's the diameter, I guess, of the circle. So what is that? It's, what is this scale? It's strange. So that's 7.5, 8 centimeters. So D is 8 centimeters. Let's get rid of the ruler. How do you get rid of the ruler? You go here and you take it away. Okay. So the radius is 4 centimeters in the diagram. So the real radius is 4 times 15, 60 centimeters, right? Or 0.6 meters. Okay, took some time, I'm sorry, but I was trying to explain it. So we found the radius of curvature. Okay, now what? We know that there is a force, a centripetal force, F, that causes this circular motion, and that centripetal force is equal to m times of the pion times v squared, let's call it m pi, times v squared over r. Oops, over r, not r squared, I'm sorry. What's that centripetal force? QVB, right? So QVB, because the velocity is perpendicular to the force, that's why we have circular motion, right? So, and the pion is positively charged inside the magnetic field that makes it undergo a circular motion, okay? And this is equal to m pi v squared over r. But suddenly we see that we have this nice cancellation, and then recognize that this is the momentum that they give us. Beautiful, right? So we solve for B that we are interested in. So B is P of the pion times Q times R, okay? And Q, this Q is E because it's just one unit of charge, okay? So let's plug in the numbers and see what happens. So the momentum is 1.1 times 10 to the negative 19, as we are told. The charge is 1.6 times 10 to the negative 19 coulombs. And then the radius is 0.6 meters, as we found. Okay, so this 10 to the minus 19 cancels. And now I have to use my calculator because I'm actually using a different radius than the radius I used in my notes. So B is 1.1 over 1.6 times 0.6. We find 1.15 Teslas, which sounds reasonable, right? I mean, this is another thing when you work through physics problems at any level in your life. Okay, this is the A level, but maybe some of you will go to study physics or engineering at the university, etc. So, for example, if you find a magnetic field of 100 Teslas, that's crazy. There is no such magnet. Maybe Florida State University has a magnet that is 20 Teslas, maybe, I don't know. But you have to have a feeling of what you're calculating. So 1 Tesla sounds reasonable. And let me check the mark scheme because they give a range of values that they accept for this B. So in their calculation, they find B to be 1.3 Teslas, but they say that the value consistent with their measured scale radius, blah, blah, blah. Okay, so they accept values for B between 0.5 and 1.5 Tesla. So we are safe, and this is a nice problem, I think. Okay, now let's move on. By the way, without the ruler, I forgot to say that, you can use your physical ruler and take this line again, and then just measure with your ruler. Yeah, you have a ruler, so you can use your ruler. Okay, so there is nothing more to say. So let's move on. Hope this makes sense. And let's move to question 16. Curling. Is anybody watching from Canada? Please write Go Canada in the comments. So, I mean, it's popular in Canada as far as I know, and I think the Nordic countries play this sport, right? It's kind of fun to watch. Maybe it's fun to play. When I was a graduate student, some friends played it, but I never tried because I don't even know how to skate, even though I tried skating once and I was successful. So I didn't fall. So curling is a sport played on ice. Players slide stones made of granite along the ice. The aim of the sport is to slide a stone into a circular area called the target. The diagram below shows 2 stones, A and B. Each stone has a mass of 18 kilograms. Stone A is moving with a velocity of 2.1 meters per second as shown. B is initially stationary. Okay. Show that the momentum of A is about 14 newtons times seconds. Okay, so PA is MA times VA. So 18 kilograms times 2.1 yields 37.8 newtons times seconds, which we assume that is very close to 40 newtons times seconds. Okay. Part 2. Stone A collides with stone B. The diagram below shows the velocity of stone B after the collision. The point of collision is marked with that X over there, not to scale. Okay. Deduce whether stone A moves in the direction shown after the collision. Okay, so we will call PA the momentum before, and let's call this PA prime, and let's call this P. Actually, I don't have to draw anything. I mean, I'm going to use what they give us there. So let's call this P. Oops, there's some leftover. So PB prime, and this is PA prime. Okay, so PB prime can be analyzed into a horizontal component, which is PB prime sine of 17 degrees, I'm sorry. And it's sine because this component does not physically touch the angle 17. Okay, that's how I remember it. Okay, and now this is the component PB prime times cosine of 17 degrees. Similarly, we have a horizontal component for A, PA prime sine of 70 degrees, and a vertical component PA prime cosine of 70. It's cramped, but I hope it makes sense. All right, so for this to work, the equations have to balance. Which equations? We have PA in the vertical direction, which is the momentum before, which is just vertical, has to be equal to with the vertical components of the momentum after. So this should be equal to PA prime cosine of 70 degrees plus PB prime cosine of 17 degrees. Okay, and since the masses are equal, we can write them down. M times VA must be equal to MVA prime cosine 70 degrees plus MVB prime cosine of 17 degrees. So M cancels. Okay, also in the horizontal direction, the two momentum must be equal to each other because there is no momentum in the horizontal direction before the collision, right? So again, momentum is conserved both in the vertical and the horizontal direction. So PB prime, actually, we already showed that the masses are equal, so we have VB prime sine of 70 degrees has to be equal to VA prime times sine of 70 degrees. Okay, so since we know that VB prime is 2, we can easily find VA prime. So VA prime from this equation, the second equation, is equal to 2 times sine of 17 degrees over sine of 70 degrees. So VA prime is 0.622 meters per second. Okay, now if, let me use a clean page. So if VA prime is 0.62 meters per second, we now go to, let's call this equation 2, let's call this equation 1. Let's plug VA prime into equation 1 and see what happens. Then in equation 1, we have 2 times cosine of 17 degrees plus 0.62, which is VA prime, times cosine of 70 degrees, must be equal to, is it equal to 2.1? Let's see. So if we plug numbers in, we find indeed it's 2.1 meters per second, which is VA. So the diagram is correct. Okay. I hope it makes sense. I hope it makes, sense. Now part B, stone A comes to rest 1.9 meters from X, the mark. Okay, the acceleration of the stone on the ice is 0.1 meters per second. Deduce whether the collision was elastic. I don't know why they give you this information. In the mark scheme, they work this out using vectors. I think it should be acceptable to just use the energies. I mean, you know the velocities and you know the masses, so there is no reason to go through complications. So the kinetic energy before, I mean, they don't explicitly ask for you to use diagrams, right? So we can just use the kinetic energy before, which is 1/2 mVA squared. So we have 1/2 times 18 kilograms times 2.1 squared yields 39.7 joules. And the kinetic energy after is 1/2 mVA prime squared plus 1/2 mVB prime squared. And if we plug in numbers, we find 1/2 times 18, times 0.62 squared plus 1/2 times 18 times 2 squared, and we find 39.5 joules. So we lose 0.2 joules, but okay, I mean, the collision is elastic. The collision is elastic. Okay. Moving on to question 17. Okay, the diagram shows a section through the components of a speedometer for a bicycle. The front wheel axle of the bicycle is connected to a cable. The cable rotates as the bicycle wheel rotates. The other end of the cable is connected to a magnet which also rotates as shown. So I guess this is the magnet over here, right? And it rotates with the bicycle. And this disc also rotates because the magnet rotates, and we will see why. Okay. All right. Okay. An aluminum disc is shaped so that it is close to but not touching the magnet. The disc is connected to a pointer by a shaft. A spring prevents the disc and shaft from freely rotating. A. Explain why the aluminum disc rotates in the same direction as the magnet. Okay, let's start with what's going on. Initially, we have this magnet, right, rotating. So its rotation changes the magnetic flux through the aluminum disc, right? So this is a long writing problem. 6 marks are awarded for this question. And in previous videos, I usually tell students that if a question is 6 marks and it's a long writing problem, you have to provide about 5, 6, 7 justification points, okay, for the argument or the question asked, okay. And also the other thing is that if a question is worth 6 marks, it should take you about 6 minutes. If it's worth 10 marks, it should take you 10 minutes. But I mean, roughly, you don't have to freak out if it takes you 10 minutes, okay? So, but timing is important in the A level. So let's start. So the first point is that the rotation of the magnet, okay, changes the magnetic flux through the disc. Okay. So what does this create? An EMF, right? So an EMF is induced in the disc. Okay. So what does an EMF create? And this is a closed circuit, it creates a current, right? So a current is induced in the disc. Okay, 3 points so far. So that current is inside the magnetic field, right? So it experiences a force. So that's the key here. So due to F being equal to BIL, comma, the current in the disc experiences a force due to the magnet. Okay. So the disc starts moving. So the disc moves in a way that reduces the flux. Okay, this is Lenz's law now, okay? So the rotation of the magnet causes an EMF, and that EMF resists the reason that created it, which is the spinning of the magnetic field, right, of the magnet. So the disk starts spinning in the same direction to cancel this movement, okay? So let's write this down. According to Lenz's law, okay, the disk rotates in the same direction as the magnet, okay, to reduce the relative motion. And when I say relative motion, I mean the relative motion between the disk and the magnet. Okay. Part B. The road speed of the bicycle should be displayed by the speedometer. Explain why the displayed speed cannot be accurate, as bicycles can have different wheel diameters. Okay, so the speedometer reading is proportional to omega, the angular velocity of the bicycle. Okay, since the linear velocity is equal to omega times r, okay, different wheels produce different velocities, since they, I'm going to use a clean page, since they might have different radii. Okay, so bicycles with different R will not give accurate readings for B. All right, part C. A cyclist has a constant speed of 8.3 meters per second on a flat road. The cyclist generates an average power of 190 watts. The total mass of the cyclist and bicycle is 75 kilograms. The cyclist comes to a hill of gradient 1 in 20 as shown. The cyclist now generates an average power of 330 watts. The speed decreases to a constant value, which the speedometer suggests is 5.6 meters per second. Deduce whether the speedometer is accurate. Assume resistive forces are constant. Okay, first of all, let's find this angle theta here, okay? So they say the gradient is 1 in 20, so 1 meter and 20 are given. So tangent of theta is 1 over 20. So theta is 2.86 degrees. Okay, in general, power is work per time. And this is something they don't really teach you at the A level, but you can prove it very easily, I would say. Maybe it's kind of straightforward. Work is force times displacement. And then we have displacement over time. So we can write power as force times velocity. Okay? So on flat road, okay, force is power over velocity. So the cyclist is using a power of, okay, let's say 190 over 8.3, so 22.9 newtons. So on the flat surface, the cyclist is using, let's say, is exerting a force of 22.9 newtons. Okay, let's go see. We still have the clean page. So let's work it out. So let's put 2 stars now. Okay, so we are continuing here. So on uphill, the cyclist, okay, exerts the same force, the same F as resistive forces are negligible, but he also needs to overcome the component of the gravity, in the direction of motion. Okay, so this is the situation theta. Let's think that the cycle is a box, okay, for simplification. So that's the weight. And we have the reaction force that we don't care about. We can analyze the weight into a component in the direction of motion that points backwards and a vertical component, okay. So this angle is also theta, okay. So that's mg cosine theta, and this is mg sine theta. Okay, how do I know that that's the case? I mean, that this angle is theta, because this side is perpendicular to this side, and then this side is perpendicular to this side, so the inscribed angles are the same. So the cyclist has to also overcome this component. So the sum of all forces he has to overcome is the force that we just calculated, this one, plus mg sine theta, okay? And this is equal to 20, what was the answer? So 22.9 plus 36.7. So in total, he has to overcome 59.6 newtons. Okay, so the power using this force is going to be power is equal to sigma F times the velocity they give us, 5.6. And if we multiply these two, we find 333.8 watts, which is exactly very close to the watts they give us, okay? Which is about the same as 330 watts. So statement is accurate. Okay, so the last problem, problem 18. At the facility for rare isotope beams, FRIB, isotopes of elements that do not occur naturally can be produced. And I have to pause here and mention that FRIB is a facility found at the Michigan State University, which is some sort of an ally to my university, the university I got my PhD from, the University of Notre Dame. So these guys have a really cool facility, and they have a cyclotron or maybe a synchrotron. I don't recall right now, but something like that. And they are able to produce exotic beams, like beams of uranium-235, for example, or beams of radioactive nuclei and stuff like that. Really cool stuff. So for those of you who are interested in nuclear physics, maybe I should make a podcast or something like that and talk about these things, because it's cool. So anyway, question A. FRIB contains a linear accelerator. The initial section of the accelerator is shown. Explain why the tubes get progressively longer. So this is a 4-mark question. So providing about 4 to 5 points is enough. So we can say that the frequency of the AC voltage is constant. Okay. As the particle accelerate, okay, so as the particles accelerate, their speed increases, okay. The time they spend in each tube, though, the time spent in each tube must be the same, okay, since the frequency of the AC voltage is constant, okay. Now, since time is length over velocity, right? If v increases, then L must increase, okay, so that T remains constant, okay? And that's the answer. So, by the way, I just told you that every has a cyclotron, or I think a synchrotron. I think it's a cyclotron. And now they say here that they also have a linear accelerator. Why? Because it provides the initial acceleration for isotopes, and then they enter the cyclotron and so on. So you can match and you can mix and match, as they say, various equipment and tools to create what you want. Okay. So, and by the way, these experiments, I mean, in these experiments they make nuclei collide with each other to produce new nuclei and exotic nuclei and stuff like that. So, question B, a uranium atom has 80 electrons removed. The uranium ion is then accelerated between two adjacent tubes until its kinetic energy is 200 MeV per nucleon. Okay, so that's a very important detail over there. Okay. Question I, calculate the accelerating potential difference. Okay, so the charge is plus 80 times the charge of the electron. Why is that? Because we remove 80 electrons, so the atom is no longer neutral, but it has 80 protons that are unpaired, right? Because 12 electrons remain, so 80 protons are not paired, so the atom is not neutral anymore, so you have a charge of plus 80 electrons. Okay, so so we can use, let me think, we have a kinetic energy of 200 MeVs per nucleon. So Q times V is 200 MeVs, which is 200 times 10 to the 6 times 1.6 times 10 to the negative 19 joules, but Q is 80 times 1.6 times 10 to the negative 19 times the voltage we are looking to find, and this is equal to 200 times 10 to the 6 times 1.6 times 10 to the negative 19. This cancels. Okay, we didn't need to do that. We could have used the fact that EV means 1 electron times 1 voltage and then just cancel the electrons, but okay, I just wanted to show you. Let me use a clean page. So we have that V is 2.5 megavolts per nucleon though, okay? But since we have 238, so V total, since we have 238 nucleons, we have to multiply this by 238 to find 595 megavolts, okay? Okay. Question 2. Show that the uranium ions will reach a velocity of about 65% of the speed of light. Okay, so we can use the fact that kinetic energy is 1/2 mv squared. So V is 2 times the kinetic energy over mass, and then we have to take the square root. So let's write this down. So we have 2 times the kinetic energy, so 2 times 238 times 200 MeVs per nucleon. We have to convert the MeVs, so 1 MeV is 10 to the 6 EVs, and then 1 EV is 1.6 times 10 to the negative 19 joules. And then we have to divide with the mass of 1 uranium-238, which is, so the mass of uranium-238 uranium is 238 atomic mass units, and 1 atomic mass unit is 1.66 times 10 to the negative 27 kilograms. Okay, so a crude estimation of the mass of any nucleus is to multiply the mass number of the nucleus with atomic mass units. Okay, it's not accurate, but if it's not given to you, you can use it. So 238 times 1.66 times 10 to the negative 27 yields 1.96. Actually, let me use a clean page. So let me use a clean page. I'm coming over here from over there. So the speed is 1.96 times 10 to the 8 meters per second. And if we divide V with C, we find 1.96 times 10 to the 8 meters per second over 3 times 10 to the 8 meters per second. Meters per second cancel, 10 to the 8 cancels, and we find 0.65, which is approximately 65.5%, the speed of light. Okay, so the statement is correct, and we are left with part C. When a uranium ion hits a target at this speed, the ion is likely to break up and produce smaller elements. One particular isotope produced in this way is magnesium-40. Okay, the naturally occurring common stable isotope of magnesium is magnesium-24, which means that magnesium-40 has 16 extra neutrons. Okay, that's crazy. Explain why the breakup of uranium-238 is likely to produce unusual isotopes such as magnesium-40. Okay, so since 238 uranium has 238 minus 92, which is the proton number for uranium. So since uranium-238 has 146 neutrons, so there are way more neutrons than protons in uranium-238. Its breakup, okay, is likely to produce neutron-rich isotopes, like magnesium-40, which has 16 additional neutrons compared with the naturally occurring magnesium-24. All right, and this was paper 1 from Edexcel from 2025. I think, what was it? Let's go to the beginning. May 2025. Let's go back to the end. Okay, I hope this video is useful. Again, I needed a change, so far I was mostly solving past papers from the International Edexcel spec, meaning Unit 1 to Unit 6 papers. But I decided to take a look into the English papers, and I saw that there is paper 1, 2, and 3. I solved the paper 2 a few weeks ago, and today I'm solving paper 1. Gradually, I might introduce more papers, but again, even for those of you guys who take the international test, this paper is very relevant because the material is very, very similar, okay? And if not identical. And one last comment about uranium-238 here. So for those of you who are interested in nuclear physics or nuclear engineering, uranium-238 is the most abundant isotope of uranium. It's 99.3% of uranium, I think, and then 0.7% is uranium-235, okay? Which is, sometimes you hear the term enriched uranium, so people find uranium-238, in nature they find uranium-238 mixed with uranium-235, but uranium-235 is just 0.7% of all the uranium found, so they enrich it, meaning that they separate uranium-238 from uranium-235, and they create reactor fuel, for example, which needs to be, I think, 35% uranium-235. So yeah, I mean, and the reason why uranium-235 is the useful one is because you can easily break uranium-235 with neutrons, whereas you need way more energy to break uranium-238. So the way I describe it sometimes is that uranium-235 is like dry wood, so it burns easily, whereas uranium-238 is wet wood, like green wood. You can still burn it, but you need way more energy to burn it, okay? So anyway, this was paper 1. Let me know if it's useful. Please tell your friends, please subscribe, and I'm gonna see you in the next one.